And now that we've gone through all that math, the future value of the annuity is almost exactly the same. So instead of looking at let me bring up my laser pointer. Instead of looking at what is the value of each annuity payment today, let's look at, well, what would the value be in the future after I'm done putting in each one of those payments? Because if I'm thinking about the last payment has had, I'm thinking about the future value at the very end, which is the time where the annuity is done. That last payment has not had any time for interest to accrue, but the previous payment has had 1 month for it to accrue. The next previous payment, 2 months to accrue, and so on and so on and so forth. So I could think of each one of those as being, well, this payment is just r, it hasn't had time for interest. This one is r times 1 plus little r, which is again the periodic interest rate as our book does it. And then the previous one is 1 plus r squared because it still had 2 months for it to grow via compound interest, and so on and so on and so forth. So looking at the formula for the future value of annuity, and our book uses S to describe the future value of the annuity, so I'm going to be consistent and use that as well. If you're wondering what's now this new S thing, it's not the same as the S for the nth partial sum from geometric series. Sorry, there's overlap. We're running out of letters, I guess. But anyways, notice it's also geometric series r times 1 plus p, r times 1 plus p squared, because each month, each one of those payments has one additional month to grow. And again, since it's geometric, I could apply the geometric series formula to that, because this is just a sum of a bunch of terms with a foreseeable pattern. And so the nth partial sum of that, I can use the formula upon, where a is the first term, r is the common ratio, and n is the number of payments. So going back to this example, r is clearly the first term. 1 plus p is the common ratio because each term is multiplied by another 1 plus p, and n is the number of terms. So if I throw all those into the general geometric series formula, we get this. And again, we can clean it up as we did with the present value of the annuity formula. So on the denominator, notice I got 1 minus 1 plus p, which is of course 1 minus 1 cancels, and the negative will distribute, leaving with negative p. And then I could multiply top and bottom by negative. So the next step, notice that it was originally 1 minus this, but I changed it to this minus 1, because if I multiply the bottom by negative, this will change, and if I multiply the top by negative, it would distribute in, which would leave me with negative 1 plus this. So, and it was just rearranged for convenience. And this leaves us with the sum of the future value of an annuity, which in the exact same fashion as the present value is often written using this ratio within the annuity S of n and p. So the future value of the annuity, capital S, is given by the payment amount times this ratio, little s to the np, where little s to the np, like little a to the np, is just that same ratio that we solved from before.